In chapter 6, we're just going to look at a couple of the topics that we haven't covered in this course. Obviously, statistical computing is a huge subject area, and we can't possibly cover all of it. What we've tried to do in this course is cover the really key ideas from statistical computing that are very much necessary for doing computational statistics. So it's interesting to reflect on the difference between statistical computing and computational statistics. Computational statistics, I would say, is a kind of a small part of the much broader area of statistical computing. So I guess a more accurate title for the course would be Statistical Computing for Computational Statistics. But even with that constraint, we still obviously can only cover a small part of the interesting things you would want to know about. So there were a few topics here that are interesting that you can read through for yourself, obviously, and look up. We're just going to look very briefly at a couple of topics we've missed. So that is sparse matrices and hashing, hash tables for fast lookups. They're both very useful things that we'll just look at very, very briefly, just so that you know that they exist. So let's start with sparse matrices. So what are sparse matrices? Well, we've seen that working with matrices, doing matrix computation is a really kind of important component of a lot of statistical computing and associated algorithms. So working with matrices is important. Sometimes when your data sets are big or you have lots of variables, your matrices get large. We can do regular matrix computations for fairly large matrices. Working with 1,000 by 1,000 matrices is now relatively straightforward on modern computers. Even, up to something like a 10,000 by 10,000 matrix is maybe doable on a high-end machine if your problem isn't too ill-conditioned. But beyond that, it's going to be very problematic for various reasons, both storage and computation. However, very often, the matrices we work with, especially big matrices, have sparsity. So very often you can formulate your problem in such a way that the matrices you work with are mainly zeros. Yeah, and that's what we mean by a sparse matrix. A matrix is sparse if most of its elements are zeros. And in that case, it turns out if you exploit that sparsity, essentially you only store the non-zero elements, then you can work with much, much bigger matrices. So, working with million by million matrices becomes, perfectly doable if that million by million matrix is sparse, and if you're using sparse matrix algorithms. That is, you're storing the matrix as a sparse matrix. You're not attempting to store all of the, billions of zeros in that matrix. You're just storing the non-zero elements, and when you do your computations involving those sparse matrices, you again do those computations in an intelligent way that automatically skips over all of the zero elements. It doesn't actually try and spend a lot of time and effort doing computations that are going to wind up being a zero. All right, so that's what sparse matrices are all about. It's about exploiting the fact that if your matrix is mainly zeros, you can just store the non-zero elements, and when you're doing computations involving those matrices, you can just do the computations on the non-zero elements. As long as you keep track of where the elements are and what elements you're going to get in your result, then working with sparse matrices can be much faster, much more efficient, involve much less storage, and that really increases the scale of problem that you can potentially work with. So let's have an example of where sparse matrices can crop up in statistics. So here we're thinking about doing a simple little regression problem, but we've got 100,000 observations, so that's quite a few observations. We've got two factors, one of which has 40 levels and the other of which has 10 levels. So that doesn't sound like a crazy big problem. But if you construct the model matrix for that, it's pretty clear that it's going to be 100,000 by 400, which is quite a big matrix. It's perfectly, doable on a regular laptop. I'm running it on this laptop, but it takes up a third of a gig in RAM, just to store that matrix. But if you look at the proportion of zeros, you see that it's actually 99% zeros. So you're storing, many, many, many zeros completely unnecessarily, and any computations you do involving that matrix will be mainly messing around multiplying numbers by 0 and adding it to the number you first thought of, which will basically not change the number you first thought of. And so almost all of the computation you do with this matrix will be wasted, and most of the storage associated with this matrix is wasted. So that's not very satisfactory. So can we do better? Well, yeah, it turns out there's a matrix library in R which supports sparse matrix computation. So let's see how that works and see what difference it makes. So if we convert that dense matrix X to a sparse version, XS, using this matrix function from the matrix library, and we compare the size to the size of X, then we see it's about 3% the size of X. So it's about 3% the storage associated with a dense version of that matrix. So obviously that's a much reduced memory footprint. That's great. It's worth just noting that it's not 1%. Why is it not 1%? Well, one reason is that you have to store the locations of the non-zero elements as well as the non-zero elements themselves. So, and there are different ways of doing that. So you can just store the indices of the locations together with the value, but actually more common would be something that's called a compressed sparse row format, where for each row you assume that most rows will have some elements. So for each row you say how many non-zero elements there are, then give the locations within that row for the non-zero elements, and then give the non-zero elements themselves. So that would be a compressed sparse row format. So there are different ways of storing sparse matrices, but however you do it, it works out pretty much the same. You're going to store something about the locations and obviously the non-zero elements, but we're still getting massive reduction compared to storing it as a sparse matrix. So we get saving in terms of storage, but we'll also get savings in terms of computing time, as long as we're intelligent about the algorithms that we use. So here's an example. If we just multiply x by y, the simple matrix vector product there, multiplying x by y or x transpose y, that takes a particular amount of time. If we do it with our sparse matrix, it's much quicker. So why is it quicker? Well, it's quicker because you just skip over all of the zero elements when you're computing x transpose y. Yeah, you don't have to do those operations. You know they're going to be zero, so just skip them and just do the non-zero ones, the ones you know are going to be non-zero. So that's why it's so much quicker. So you save on storage and computation time. So you could think about implementing this yourself. It's not so difficult to implement what we've talked about so far. It's a nice little programming exercise to do that. Where sparse matrix computations become tricky is when you want to start solving linear systems, which obviously we very often want to do. And for that, you need to start doing decompositions, right? We know that that's a good way for thinking about how to solve linear systems. We'll look just at the Cholesky decomposition here because we know that that's the simplest decomposition we've seen. And we'll see the problems that arise when you start doing these decompositions in practice. So you can take a sparse matrix and you can do a Cholesky decomposition. That Cholesky decomposition will, in general, in principle, have zeros in it. So it will have some degree of sparsity. The problem is that typically, if you're not very careful, the Cholesky triangle will be much less sparse than the matrix that you started with. And so the extra elements that you get that are no longer sparse, they're sometimes known as infill or sometimes fill-in. Yeah, so you get obviously non-zero elements in most of the places where you had non-zero elements in the original matrix, but you also get more non-zero elements, and these are the so-called infill or fill-in. And if you're not careful, you'll get a lot of fill-in, as we're about to see. Okay, so if we look at this, we can take x transpose x, that's a 400 by 400 matrix, and we can do a Cholesky decomposition. So we can do that on the dense version or the sparse version, whatever. So if we do that on the dense version here, we've got this 400 by 400 matrix. We can check the proportion of sparse the proportion of zeros. The proportion of zeros is about 98%. So X transpose X here, this 400 by 400 matrix, is 98% zeros. So this is a very sparse matrix. This is all good. This is very much in the sort of realm of sparse matrix theory. We can actually just do a little image of the non-zero elements. That can be quite a useful thing to do, just to visualize what's going on with your sparse matrix. The way the image commands works, you'd sort of want to flip the rows. You'd want to reorder the rows. So this bottom left here is really the top left of your matrix. Yeah, and this is the matrix diagonal. So that's a bit confusing. I should really flip the rows, but you get the basic idea. So this is the sparsity structure. So the yellow represents the non-zero elements and the purple represents zero. So you see that almost the whole matrix is zero. There's just the diagonal and a few other off-diagonal elements that are non-zero, but most of the matrix is zero. Okay, so that's great. That's exactly the kind of thing you would want. We can check our Cholesky triangle to make sure it works, and it does, so that's all good. But if we start looking at the number of non-zero elements, it's a lot. So we've got a lot of non-zero elements in this Cholesky triangle, so that's not good. And again, we could just do a little image to look at that. So here it is, and remember the yellow or cream, the non-zero elements. So this is our Cholesky triangle. Again, it should be kind of flipped, but you get the basic idea. And you see that it's basically dense. So that's not good. The actual triangle is dense. You see there are a few little purple spots maybe, but so there are a few zeros in it, but essentially it's dense. So we've lost all of the sparsity. So any subsequent computations we do now, we've got this sparse Cholesky triangle. It's we can't do sparse matrix operations, and so all of the benefits that we might have of doing sparse matrix computations have just been lost. So that's a bit of a disaster. So is that inevitable? No, it's not inevitable, because it turns out that the amount of fill you get depends very sensitively on the order of your rows and columns of your original matrix. So basically a diagonal matrix, you won't get any fill in whatsoever. And so what you want to do is to try and permute the rows and columns of your sparse matrix to make it sort of as diagonal as possible, to reduce its so-called bandwidth as much as you can. So the trick of finding permutations of rows and columns is potentially a very hard problem, but in fact there are pretty good heuristics for doing it, and these are called fill-reducing permutations. So what you really want to do is do a fill-reducing permutation, then do your Cholesky decomposition, but then keep track of the fact that you've permuted the rows and columns in any subsequent computations that you do. Otherwise you'll end up with all of your rows and columns messed up. And that's a very common source of bugs in sparse matrix code. So let's just see what happens here. So this library, fortunately, supports pivoting. So if we do want to do a Cholesky decomposition of a sparse matrix, we can just request a pivot. And like I said, what that will do is it will figure out an optimal pivot, an optimal permutation of the rows and columns. Then it will carry out the Cholesky decomposition and it will return the result. Now that is of course not the only thing you need to do to know. You also need to know what that permutation was. So that's stored in this pivot variable here. And so if you're comparing your kind of recomposed Cholesky decomposition with your original matrix, you obviously have to permute the rows and columns of your original matrix before you do the comparison, otherwise they'll be completely different. Yeah, but if we do that in the right way, then we can see that the Cholesky decomposition has worked. Okay, so what we get back from this Cholesky decomposition is both of the Cholesky triangle, but we also get the pivot variable, the permutation that was used prior to the Cholesky decomposition. So that's a little bit of a hassle, and it can make your code a little bit more fiddly, but the benefit is that when we look at the Cholesky triangle, it's very, very sparse. Yeah. So remember, purple are zeros, yellow is non-zeros. So we've got the diagonal, we've got a few little non-diagonal elements, we've got a few little elements here along what is actually the bottom of the matrix. So we've got very, very few non-zero elements in that Cholesky triangle, right? So compared to having a dense matrix, we've now got a very, very sparse matrix. And so again, a subsequent like forward or backward solve, we could use a sparse matrix version of a forward or backward solve and get massive kind of speed ups as well as storage savings by doing that. Okay, so sparse matrices are good, but there are some complications you need to be aware of in order to maintain sparsity throughout your computations. So if that's all you want to do, then that R matrix package is pretty good. So if you just want to do some basic sparse operations, Cholesky decomposition, forward and backward solves using the Cholesky decomposition, as long as you use pivoting, then that's actually pretty good. If you're going beyond that, you really need to do a bit of research to see whether the algorithms that you're using in R are really state of the art, and do your own testing and benchmarking for how good you think they are. Yeah, so R is not necessarily the best place to do computational statistics at all, actually, and that's going to be the subject of the bonus lecture. But if you are working in R, figure out what's going on, and just be aware of the fact that there are obviously other matrix libraries around, other sparse matrix libraries around that you could have a look at to see how they're doing. Okay, so obviously there's lots more to say about sparse matrices, but we're running out of time now. So just one final topic that's worth knowing about, the idea of doing fast lookups. So very often you want to store stuff in memory with a key and be able to look it up later very quickly by that key. It's something we actually just take for granted. There are lots of ways to do it, and in fact in R there are various different ways you can look things up by name or by key very quickly, and so we often don't think about it, but there is a cost associated with doing lookups, right? What you don't want to do is store things linearly in memory, and every time you look it up, go through all of the keys one at a time until you find the key that you want, and then pull the object out at that location. That would be the naive way to do lookups. That's very, very slow. It's an order n operation depending on the length of n of your list. And you really don't want to be looking things up like that. You want to use much smarter ways to look things up. So how do you do it? Well, hash tables are the basic answer. Incidentally, these go by different names in different places. So in Python, if there are any Python people, these are just Python dictionaries. And kind of the whole zen of Python is that everything in Python is a dictionary, including namespaces. And we'll see that in R, actually, your environments can be hash tables as well, but in Python basically everything is a dictionary. Dictionaries are used all over the place, and dictionaries are hash tables. Okay. So what is a hash table? Well, the idea is you have something that you want to store, you want to give it a name, and you later want to be able to retrieve that thing by using the name. Yeah, so that's it. So obviously we've just said the naive way to do this will be to store the names in a sequential list, the values in a sequential list. If you want to look something up later by its name, you go through the list of names until you find it, you get the index of that thing, you then know the index of it in the other list, and then you can pull it out like that, right? So you could do that, but that's very slow, so you want a fast way to do it. So it turns out that those ideas from pseudo-random number generation we talked about previously can be used to actually give a neat solution to this problem. So what you do is you take your key, you turn it into some sort of seed for a random number generator, you then run that random number generator forward for a while to get what is essentially a completely random key derived from that original key. And the idea is that it's a purely deterministic operation. So if you were to do this again with the same key, you would obviously get the same hash, but the hash you get is essentially random and essentially uniformly distributed in the space of possible hash values, because it's been made with ideas from pseudo-random number generation, where that was exactly the requirement we had there, which was you got a number that looked uniform. Okay, so we're using exactly the same idea here, but we're crucially using the fact that it is deterministic and the result looks completely random, uniformly random. Yeah. So whatever hash value we put in, we get the same hash value out. Whatever key value we put in, we get the same hash value out. But if we were to put in a slightly different key, we would get a completely different hash value out that would just be completely unrelated to the hash of the closely related key. Yeah, because this random number generation process would split those keys apart in hash space. Yeah, so whatever set of keys we have, our hash values are going to look like uniform random numbers over our space of hashes, over the size of our hash table. Yeah, so we decide on the size of our hash table and we end up with hashes that are uniformly distributed over the size of that hash table. And so the advantage of that is you spread everything out nicely, and so you can just directly store the values associated with a key at that position in your hash space. Now, if your hash table isn't huge, then there is a chance that you will end up with two different keys being assigned the same hash number, the same index in your hash table, and so then you'll have to resolve that, and you could do that any way you like, including by the naive linear search strategy. That's fine, because you're only going to have a small number of clashes if your hash table is a sensible size. So that's the idea behind hash tables. Yeah, you take your key, you turn it into a random hash that that hash value is uniformly distributed in hash space, so you can use that as a location by which to store the value that you're interested in. So when you want to look that up later, you can just run this hash function and go immediately to where the item is. You don't have to linearly search through anything in order to find it. And so this idea of hash tables crops up all over the place because you very often want to look things up by name. Okay, so how do you do that in R, if you want to do that in R? Well, I've already told you that in Python, everything is a dictionary, including namespaces. I think in R, by default, the environments are not hashes, but you can request an environment that is a hash table. Yeah. So if we create a new environment, hash table, with a new m function and request it to be a hash table, then that's it. HT is a hash table. So we can assign values to it using a key. So here we're assigning the value bar using the key foo. We can also assign a list, a numeric vector, in fact, of numbers using the key baz, etc. And we can later retrieve something that we're interested in. We can retrieve foo and find that the corresponding value is bar. All right, so an R environment is very much like that, right? You store things by name and you later retrieve them by name. Yeah, you've maybe not thought before about how that works or why it works or what the mechanisms are, but one way you can do it is via a hash table. Yeah, so we can get values back by name at a later date, and the point is that even if we had millions, potentially tens of millions of these keys and values, we could essentially instantly get back our value associated with a given key without doing some very naive, slow lookup operation, right? That's the whole idea. So what's all of this got to do with statistics? Well, it turns out there are all kinds of things we do in statistical computing where we want to store things by name and look it up by name at some later time. So we just got one little example here, which is doing triangulations in spatial statistics. So you might want to triangulate a region, and to do that, you need to know the triangles that are adjacent to your existing triangle. So you're sat at some particular triangle, you want to know that the triangles that are adjacent to it. Well, how do you know that? Well, the triangles that are adjacent to it will share an edge. Yeah, so you look for the shared edge. How do you look for the shared edge? Well, you have a hash table that has any unpaired edges and a pointer to the triangle that they correspond to. So when you're doing your triangulation, you can be constantly looking up edges, right, by name. So in this hash table, the unpaired edges are the keys to the hash, and the associated triangle is the value. Yeah, so you can look up triangles by edge very quickly using a hash table, right? So that's just one example, right? There are billions of examples like this, but that's just one example of where in statistical computing, the ability to have fast, efficient lookup mechanisms is very, very handy. Okay. So that's basically it for the formal part of the course. If you want to know a bit more about sparse matrices, there are a few links there. But what this is really telling us is that there's a whole world of computing science and algorithms that's very relevant to statistical computing. So if you want to know a little bit more about what algorithms there are and how they can be useful for solving interesting computational problems, then some introduction to algorithms, like maybe this one, would be something worth knowing about. Okay, so this is the end of the formal part of the course. This covers the syllabus. All right, so we've covered the syllabus of the course now. So this is everything you need to know for example, the end of course assessment and the practicals and exercises and things. So that's it for the formal part of the course. There is one more lecture. Each time I've given this course, I've finished with a bonus lecture on the future of statistical computing. So I strongly recommend that you watch that. In that lecture, we'll talk about what's wrong with statistical computing as we've presented it, what's wrong with R as a language for statistical computing, and how we might do statistical computing better in the future. So like I say, it's optional, but I highly recommend that you give it a watch. All right, thank you.